Okay, now let's talk about section 2.5. Section 2.5 limits supremum and infimum. Okay, as we have discussed in the previous section, a sequence converges to a point if and only if it is a Cauchy sequence. Even you add the extended real number infinity, we know that not every sequence convergent, right? So let's talk about some related concepts about the limit for every sequence. Okay, so you have a sequence. For example, you have a sequence x1, x2, x3, x4, and so on. And then we construct the following sequence. S1 is the supremum of x1, x2, and so on. So we write it this way. The supremum of xn, n is greater than or equal to 1. So we talk about supremum, all of them, and we construct a T1. Here we discuss infimum of all of them. It's infimum n greater than or equal to 1 xn. And because we talk supremum and infimum, supremum could be infinity. It belongs to the extended real numbers. The infimum could be negative infinity. Okay, so S1 belongs to R plus infinity, R union infinity. T1 belongs to R union negative infinity because it's infimum. Okay, it's not to be infinity. It can never be infinite because it's less than x1, less than that. And then we continue this. We define S2. S2 is a supremum. Here, we ignore the first term. We start from second term. N is greater than or equal to 2. Xn. Again, it belongs to R union past infinity. And T2 inf x2. The inf n greater than or equal to 2 xn. It belongs to R union negative infinity. So we continue this for Sn. What is Sn? Sn, we start from xn, xn plus 1, and so on. We compute the supremum. Supremum always exists when you talk about the extended real numbers. If it's not extended real number, unbounded subset has no supremum. We're talking about extended. So it is a supremum of k greater than or equal to n xk because we use n here. And Tn is the infimum of xn, xn plus 1, xn plus 2, and so on. It's infimum k greater than or equal to n xk. Okay, so either case, it belongs to R union positive infinity, here R union negative infinity. Okay, and from this construction, we can see that you consider less elements, of course, the supremum will not increase. So this Sn is a decreasing sequence in the extended real numbers of extended real numbers. Maybe you have infinity, 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 all infinity in this sequence. Of course, at any position, if you do not have infinity, the rest of the term will not be infinity. It could be a complete sequence of infinity. That's possible. It could be a complete sequence of infinity. But if at certain position the term Sn is not infinity, then the rest of the sequence the rest element in the sequence, the rest elements in the sequence are not infinity. Are not infinite because it's a decreasing sequence. Once this one is not infinite, it's a number. Rest element of the sequence will be numbers. It will be less than that, right? Okay. The same. Similarly, Tn, you consider less element, infimum will increase. It does not decrease. So Tn is an increasing sequence. Tn will increase because you are talking about infimum. Less element give you bigger infimum of extended real numbers. It could be negative infinity all the time, all the places. It could be a complete sequence of negative infinity. That's possible. And similarly, same thing, if at a certain position the term at Tn is not negative infinity, then the rest element in the sequence are not negative infinity, right? They're bigger than that number. It's increasing. Okay, so this is the observation when we define this new sequence. Because it's always a monotone, increasing, decreasing. Remember that we have the monotone convergence theorem. So for the sequence Sn and Tn, they have the limit in the extended real number system. Okay, so we have this definition. Okay, arbitrary sequence. Let Xn be a real sequence. Xn be a real sequence. Then the limit supremum of Xn is the extended real numbers, not as extended real number. The lim sup is n to infinity Xn. By definition, it is a limit of the supremum, actually Sn, k greater than or equal to n approaches infinity. It is just a limit of Sn, the limit of the supremum. It's a decreasing function. It's a decreasing. Supremum, sequence of supremum is a decreasing function. And the limit infimum of Xn is the extended real number lim inf n approaching infinity Xn. It is a limit of the infimum k greater than or equal to n xk. approaching infinity. Right? Okay. Okay, now let's continue the discussion about the limit of this Sn. So let's discuss the cases. Case 1, if Sn is infinity for all n in the natural numbers, then the lim sup of Xn n approaching infinity, of course, is infinity. Okay, so if you have constant infinity, then it's going to be infinity. Case 2, if Sn is not constant infinity for all n belong to n. So remember I mentioned if at a certain position it's not infinite, then rest element of the sequence is not infinite. Okay, if this happens and we have situation Sn, and if Sn is bounded below then the lim sup bounded below means it's a bounded sequence. Decreasing bounded lim sup Xn is a number. Number means just regular number. Case 3, if Sn is not equal to infinity for all n in n, and if Sn is not bounded below, if it's not bounded below, then the lim sup of Xn will be negative infinity. Lim sup Xn will be negative infinity. Let's see the examples about each case. Okay, so for this one, you can just choose Xnbn. Xnbn, then you can check that the supremum of Sn is going to be infinity all the time. You have 1, 2, 3, 4. This sequence for each subsequence, you ignore first few terms. The supremum is always infinity, so it's infinity. And the lim sup here, you can just randomly pick up. For example, you choose Xn to be -1 to nth power. And this one, the Sn is constant 1. Sn is constant 1. Check this. Then the lim sup is 1. Here the lim sup is infinity. In this one, you just choose -1, -2, -3. Then Sn is equal to -n. S1 is equal to -1, S2 is equal to -2, Sn is equal to -n, but it's not bounded below. So the lim sup of -n approaching infinity is -infinity. Right? So that's the 3 examples about the 3 cases. Three examples about 3 cases. Okay, of course, we have 3 cases for the lim sup. We also have 3 cases for lim inf. Case 1, if Tn is constantly -infinity for all n in the natural numbers, then the lim inf of Xn approaching infinity is negative infinity, right? That's case 1. And this case is exactly this case. Like for the case 1, the example could be here. And let's put here. This is example 1, example 2, and example 3. Let's put example 3 here. In this example, the infimum is always negative infinity, so the lim inf is negative infinity. Case 2, if Tn is not negative infinity for all n in n, it's not a negative infinity, so start from one element is going to be a real number. And if Tn is bounded above then the lim inf xnn approaching infinity is a finite number. You put E2, the second example, you can put it here. And the case 3, if Tn is not equal to negative infinity for all n in n, and if Tn is not bounded above then the lim inf xn approaching infinity is going to be past infinity. What is the example? E1, the example 1. For this one, the lim inf is lim supremum is infinity. Infimum is n. N will approach infinity. So the lim inf could be past infinity. See, that's all 6 cases, and those 6 cases actually have 3 examples to represent. All right. In the textbook 2.33, they ask you to do the situation xn equal to -1 to n. That's this one. The second example, we already discussed the lim sup is 1 and the lim inf is -1 because when n is odd, it's always -1. So the infimum Tn is always -1. It's constant. And 2.34, if you have xn equal to 1 plus 1 over n, 1 plus 1 over n, you will see that the supremum of 1 plus 1 over k, k is greater than or equal to n. The supremum, you choose a smaller one. It's a 1 plus 1 over n. And the infimum of 1 plus 1 over k, k greater than or equal to n, is equal to 1. You let n approach infinity, this becomes smaller and smaller, this is a 1. So the lim sup of xn is 1, and lim inf xn is also 1. Is also. All right. So you have to play with infimum and supremum about some simple sequence. Okay, now let's see the lim inf lim sup with the original convergent sequences. Okay, so here it's a new concept. It works for all the sequences. It's not just for bounded sequence, monotonic sequence. No, it's not that. This lim sup lim inf can be defined for arbitrary sequence, so that's an advantage. How can we relate this lim sup lim inf with the original convergence or original limit. That's the theorem 2.35. Okay, so let xn be a sequence of real numbers and let S be the lim sup xn and T be the lim inf xn. Okay, then there are subsequences x and k, k in n, and x lj, j and n, two subsequences such that the x and k will approach s as k approach infinity, and x lj will approach t as j approach infinity. Okay, so the lim sup, lim inf are the limits of certain convergent subsequences. Okay. Let's check. In the book, they prove the situation, the result for the lim supremum. Yeah. Okay, very good. Now let's prove it for the lim infimum. We will prove the result for the lim infimum and see how we get it. Okay? Okay, so check here. We have three cases. The proof depends on those three cases. We know that we have t. Okay, proof. We have a tn equal to the infimum k greater than or equal to n xk, and tn increases to t as n approaches infinity. Okay, that's increasing. So let's see. Case 1. If this t is negative infinity. If t is negative infinity, this implies that Tn is negative infinity for all n. Okay, that's exactly the first case. Yes. Okay. Okay, it's a negative infinity for all n. Then let's check. T1 is negative infinity. It means there is n1. There is an n1 such that xn1 is less than negative 1. Okay, so that's the first step. And otherwise, it's a bound. Okay, and then for t2 equal to negative infinity. not a T2 negative, this one, sorry, my bad. Let's choose T, here is N1, right? There's N1. I want to exclude this N1. This N1 is already considered. Let's put N1 plus 1. Okay, N1 plus 1, it means you start from N1 plus 1 and consider the rest of the tail. So you exclude N1. Tn1 plus 1 is negative infinity. So there is an N2 such that xn2 is less than negative 2. This time I choose negative 2. So here we can see N2 is strictly greater than N1. Okay? And then we talk about Tn2 plus 1. I already consider N2. I ignore N2, start from N2 plus 1. Tn2 is negative infinity. There is an N3 such that xn3 is less than negative 3, and we get N3 is greater than N2 is greater than N1. Continue this process. We have N1 less than N2 less than N3 less than N4 infinity with, and xnk is less than negative k. Xnk is less than negative k. Okay, then what do we have? We have the limit of x and k is negative infinity, k approaching infinity. Right? So that's a proof. So every time we choose one, but once you choose one, you are going to exclude it from the next selection. How do I exclude this N1 from next selection? You just start from the N1 plus 1, the next one. Because every Tn is negative infinity, so you can always do this process. Right? Okay, so that's a case 1, when you have the lim inf equal to negative infinity. Case 2, if t is a positive infinity. If the lim inf is a positive infinity, then what you have? Then Tn is not equal to negative infinity for all n in n, and Tn is not bounded above. It's not negative infinite all the time. If it's negative infinite all the time, t will be negative infinity. And if it's bounded above, it will not be infinity. All right? Okay. Okay, now let's see. How do we proceed it? Without loss of generality, without loss of generality, here, this long word, we later will write WLOG. Okay, without loss of generality, we assume that Tn is not equal to negative infinity for all n. If it's for some, not for all. I make mistake? For some, the logic is wrong. Okay. For some. Sum, my bad. It's better to use sum, not to use for all. Okay, now it's a for all, so I don't see any negative infinity. I don't see any negative infinity. And then I'm going to construct a number. Okay, and the Tn is not bounded above. Okay, so Tn is not bounded above, then for m equal to 1, there is an n1 such that Tn1 is greater than 1. Tn1 is greater than 1, right? Okay, so xn1 will be greater, so xn1 will be greater than Tn1, greater than or equal to n greater than 1. Okay, so that's one thing. And then for m equal to 2, because it's unbounded above, it's not bounded above, there is an n2 such that n2 is greater than n1 and Tn2 is greater than 2. Tn2 is greater than 2. Right? How do I know I can find this n2 greater than n1? How do I know I can find n2 greater than n1? Because this Tn is an infimum. You start from the when I talk about this Tn2 is the infimum. I don't think I need to explain it, because it's increasing definitely some the rest of the stuff positions, it has a bigger numbers, correct? Remember that for if the limit of xn is past infinity, it's equivalent to say for any capital M there exists n such that for all n greater than or equal to capital N, xn is greater than or equal to m. This is the definition. And when you do this for m equal to 2, you select n and also you select this n greater than n1, then it works out. So I don't think this is a big deal. It's just part of the definition. Okay, so I get Tn2 is greater than 1. You continue this. We have n1 less than n2 less than n3 less than infinity with Tnk is greater than k. Tnk is greater than k. Okay, this condition comes from your assumption T is the limit inf is infinity, so you can always have it. And one of the important properties is that x and k is greater than or equal to T and k is greater than k. So the lim x and k approaching infinity is equal to infinity. Correct? So T is the infimum. Every element will be greater than it, or greater than or equal to it. So x and k will work out. Okay, so those two are the extreme case. Now let's see the case 3. The T is between negative infinity and the positive infinity. Also, if T between negative infinity and positive infinity, then Tn cannot be constant infinity. So without loss of generality, we assume that Tn is not negative infinity for all n in n. Okay, so all the numbers, the infimum are numbers, and the limit of Tn approaching infinity is t. Limit of Tn approaching infinity is t. Okay, so what we have, it's increasing, remember. Increasing, so for any epsilon greater than 0, there exists capital N in natural numbers such that for n greater than or equal to capital N, t minus Tn is increasing to t. This symbol looks like this, so up's value is just t minus Tn. It is less than epsilon later. Let's put epsilon over 2. Epsilon over 2. Okay, so we have this. All right, now let's check the other part. Tn is the infimum of xk k greater than or equal to n. Correct? And for the same epsilon, there is a k greater than or equal to n such that, remember this is infimum, such that x nk, let's put nk, n sub k, x n sub k is greater than or equal to Tn less than what? Less than Tn plus epsilon over 2. Less than Tn plus epsilon over 2. Yeah. Okay. So combine these two, what we have? We have T minus xnk. It is T minus Tn plus Tn minus xnk. By the triangle inequality, it's less than epsilon over 2 plus epsilon over 2 is epsilon. So basic idea is that Tn is close to T and xnk is close to Tn. So you use a triangle inequality, 2 steps to get it. Okay. So one tiny thing is that how do I know every time I do not get the same nk? How do I know I don't get the same nk all the time? In order to get that, we are going to modify this proof a little bit. We have some quantitative versions so that I can clearly say this nk are not the same for the different n. Okay, so for every n greater than for every n in the integer, I'm going to consider epsilon to be 1 over n. Epsilon becomes smaller. Okay, so okay, this way. So for every n belong to the integer. So for example, here n is a 1. There exists n in the natural numbers such that for n greater than or equal to capital N, let's put n1 here. Then t minus t n equal to t minus tn less than, here I do not use epsilon. Remember this n is equal to 1, I put a 1/2. And similarly for this, for t capital N sub 1, it is the infimum of xk, k greater than or equal to n sub 1. For the same epsilon, there is n1 greater than or equal to capital N1 with x n1 greater than t capital N1 less than t capital N1 plus 1/2. So combine these two, we get we have t minus tn1, this xn1, t minus xn1, this xn1 less than 1/2. This is one thing. And then for n equal to 2, there exists n2, so that n2 in n with bigger, better, with n2 greater than n sub 1, greater than n sub 1. By this method, I can say that my next selection will not be xn1 again. You see, this is quantitative stuff. Next time it is not n1, little n1. For this n2, there exists n2 such that for all n greater than or equal to n2, we have t minus tn less than, here you are going to get 1 over 2 times 2 is 1 over 4. Here is a 1 over 2 times 1. Okay, and then you will get blah blah blah, you will get the t minus xn2 less than 1 over 4. So continue this process. We can find a sequence of nk such that what? So n1 less than n2 less than n3 less than n4 with t minus xnk is less than 1 over k. Always. T minus xnk is less than 1 over k all the time. Okay, and this will imply, so the limit x and k to infinity is equal to t. Okay, so we have the proof. All right, so we need the quantity so that we can exclude this n1 every time. Every time we exclude n1, exclude n2, exclude n3. Okay, so this is the proof for the what? Here's the idea. So this place I actually have two parts. The first part is about the epsilon and the capital N. But in this epsilon capital N, I couldn't explain why this nk does not repeat. Why this nk does not repeat? For every epsilon, for every n, you always have the different nk. I don't know how to claim this. And in order to claim this, so every time you have for different epsilon, you have a different n. For different n, every time you move it, you shift it. So that's a quantitative way to claim that. Right? Okay, whenever you have step by step, you can construct a sequence of different elements. Okay, so that is the relation between the lim-sup, lim-inf, and the convergent subsequences. And now let's see a connection between the lim-inf, lim-sup with the regular limit. So 2.36 theorem. let xn be a real sequence and x be an extended real number, then xn converges to x as n approach infinity if and only if the lim sup of xn n approach infinity is equal to the lim inf xn n approaching infinity equal to x. Okay, so this feels like the left limit and right limit sense, but it's not from the direction, it's from the direction of value, upper supremum if. Okay, so here we have to allow the extended real numbers because we discussed the supremum and infimum for a general sequence. Okay, this is proof. Two directions, this is if and only if. Suppose that xn approaches x as n approaches infinity. Okay, then all subsequences x and k with x and k will converge to x as k approaches infinity. A convergent sequence have all convergent subsequences to the same limit. And we just proved that the lim sup lim inf are the limit of certain subsequences. So by the previous theorem, we know that the lim sup of xn and the lim inf xn are both equal to x. Right? It's done. Conversely, suppose the lim sup is equal to lim inf equal to x. Then we have x is extended real number. We have two cases. More than two cases, actually three cases. Positive infinity number, negative infinity. Okay, so case one. X is positive infinity. X is positive infinity, it means Sn is constantly infinity and Tn is not bounded above, right? This x lim sup is positive infinity, then the supremum is always constant infinity. Lim inf is positive infinity, then it's not bounded above. So Tn increases to infinity as n approaches infinity. Tn increases to infinity as n approaches infinity. That make everything clear. So for every m greater than 0, for every m in R, there exists a capital N such that for all n greater than or equal to capital N, and Tn will greater than or equal to m. Tn is an infimum, so xn will greater than or equal to Tn greater than or equal to m. So for every m there is a capital N. For all n greater than capital N, xn is greater than m. So the limit of xn is positive infinity. That's exactly the definition about positive infinity, right? Okay. So that's a case 1. And the case 2, if x is negative infinity. X is negative infinity, remember first, all the Tn's are negative infinity. And the Sn is not bounded below. Sn is not bounded below. So Sn will decrease to to negative infinity. Decrease to negative infinity as n approaches infinity. So let's see, for every m in real numbers, there exists a capital N belong to the natural numbers, such that for all n greater than or equal to capital N, Sn will be less than or equal to m. Sn is the supremum less than m. So all xn will be less than or equal to Sn less than or equal to m. So the limit of xn is negative infinity. Okay? So you use the supremum to control it and push the roof to the negative infinity. This first case, means you lift the floor to the positive infinity. And third case, assume this x is a number, not infinity. X is a number, then for any epsilon greater than 0, there exists a capital N in the integers such that Sn is a decreasing, so the Sn minus x is less than epsilon over 2, and t is increasing, so x minus tn is less than epsilon over 2, right? It's increasing to x. Sn is decreasing to x. Okay, then what we have? Then we have for n m greater than this capital N. And m greater than capital N, let's talk about xn minus xm. Xn minus xm. Those two quantities, one is bigger, one is small. So assume, it doesn't matter which one. Assume xn is less than xm. Then this one is equal to xm minus xn. m minus xn. So supremum, this one is less than or equal to Sn. Sm is less than Sm. This one is greater than x. Hold on a second. Xn is greater than the inf Tn, but negative, it's still less than inf Tn. It's less than inf Tn, right? Correct? This one is less than it. This one is greater than it, but with negative sign, it's also less than. And Sm, let's put Sm minus x plus x minus Tn. Sm minus x, when mn both greater than capital N, Sm minus x is less than epsilon over 2. X minus Tn is also less than epsilon over 2. So this is exactly epsilon. What did we prove? We showed that Xn is Cauchy sequence. We show Xn is a Cauchy sequence, then Xn converges to X prime for some number X prime in R. So all its subsequences converge to X prime. But we know these two the lim sub, lim inf converge to X, then X is equal to X prime. Right? So we are done.